Okay, in this section we're going to learn about the theory of a wave, and this is the beginning of the quantum theory of the atom. So in the early 1900s and actually late 1800s, the scientists knew that atoms were made up of protons, neutrons, and electrons, and they knew that the electrons were outside the nucleus, but they didn't know what they did and what space they took up. But they did burn a lot of things, and they kind of started recognizing the fact that different metals gave off different colors. And that's basically the fundamentals of what we're going to be talking about for this entire chapter. And in order to do that, we have to understand something about light. So light is a wave, and a wave is simply a repeating change in matter or physical property or physical field. And so this is showing the oscillation of a field going up and down, which is the repeating change. And so the distance from here to here is one wavelength, and I'll have all these here. And so that stays constant in this wave. Light, however, is an electromagnetic wave, which means it has an electrical component and a magnetic component that oscillate through space and time. And in theory, I have a video here. It's going to take me to a video. It's very short. And so what you see here is that one component is electrical component, and it's moving along this line, and the blue line, which is at 90 degrees, is the magnetic component, and it's moving through also. Oops, that was a very short video. Get back there. Okay. So as I described before, a wavelength is simply the distance between, I pointed out the crest or the top of the waves. Also commonly used is the troughs or the bottom of the waves. But technically it's any two identical distances. So if I wanted to, I could measure, well, I don't want to use that color on a blue wave. Okay. So I could measure from here, whoops. That's what I get for not using my pen. From here to here in my way of drawing, which is why we typically don't use them, and this would also be the wavelength. And wavelength is symbolized, this is called lambda. Okay, and it's the upside down U, or Y. Upside down Y. Frequency is another characteristic, and it's symbolized by nu. So these are in U. These are Greek letters, okay? And I write it as kind of a funky looking V, okay? This is how the generation of text makes it look like, but this is how I handwrite it. And so it's the number of wavelengths that pass a fixed point in 1 unit of time. The units are hertz or per second or 1 per second, or this also can be written as s to the minus 1. These two things right here are equivalent. So here's showing the fact that I have two waves. So here's wave 1 and here's wave 2. So this is two waves. And this has been denoted as being 1 second. And so it has a hertz of 2 hertz. 2 waves per 1 second. Whereas this has 4 waves. Here's 1, 2, 3, 4. So 4 waves. And the same amount of time of 1 second. So this has a frequency of 4 hertz. Now, what can you say about the relationship of the frequency to the wavelength? What happened as I increased? So if I increase nu, what happened to lambda? It got shorter. So there's an inverse relationship to the lambda and the nu. As one goes up, the other one goes down. Okay? So now, the last thing we need to talk about before we start doing problems is the speed of light, which is symbolized by c. Okay? So that's the speed of light there. Okay? And it's the speed of light that moves through different materials. And so we're going to use the one through a vacuum. A lot of times you will see that 2.998 times 10 to the 8th meters per second, and that's air. when I round this to 3 significant figures, it still rounds to 3. So I tend to use this number. If you use this number, that's fine also. This is a vacuum. I have to look at how to spell vacuum. And this is air, but when I round them to 3 significant figures, they're the same value. And so from that, I get this formula. The speed of light, c, is equal to lambda. So this is speed of light. This is wavelength, or lambda. And I usually say lambda and nu. And this is frequency. And so this is the formula that we're going to be using here to calculate one of these. So the problem is, what is the wavelength? So just like we've been doing all semester, so it wants to know what lambda is. If I have a frequency, and frequency symbolized by the nu, of 3.76 times 10 to the 14th seconds to the minus 1. So the formula that relates those two is c is equal to lambda nu. And so, like I said, I use 3.0 times 10 to the 8th. Lambda is what I'm looking for, and my nu is 3.76 times 10 to the 14th. I'm going to divide both sides by this 3.76, so 3.0 times 10 to the 8th divided by 3.76 times 10 to the 14th is equal to lambda. And so lambda then is 7.98 times 10 to the minus 7th meters. Okay. And so the unit for lambda in standard is meters, which is the distance, or the SI unit for that. Here's another problem. This time it wants to know what is frequency. Frequency is nu. And it doesn't describe this, but I have the unit of meter. And if I have the unit of meter and I'm talking about frequency, we're going to use lambda. So 6.9 times 10 to the minus 13th meters. So again, it's going to be c is equal to lambda nu, or 3.0 times 10 to the 8th is 6.9 times 10 to the minus 13th nu. I'm going to divide by the 6.9, so 3.00 times 10 to the 8th divided by 6.9 times 10 to the minus 13th is nu. So nu ends up being 4.35 times 10 to the minus 20th hertz. It could also be written as 4.35 times 10 to the minus 20th per second. Or again, one more time, 4.35 times 10 to the minus 20th seconds to the minus 1. So basically, all three of these units are valid units for hertz. I suggest that you try this on your calculator to make sure that you got this. If not, go back to chapter 1, the video where it talks about scientific notation, and the video about how to enter this into your calculator so that you get the minus 20. If you got a positive 5, then you didn't enter this part in the denominator correctly. Okay? So the electromagnetic spectrum is a range of frequencies. You have gamma rays, okay, and they're very small wavelengths, to X-rays. So this is actually a nuclear radiation. X-rays, of course, if you go to the doctor to see about a broken bone, it's an X-ray. Ultraviolet, talking about the sunlight. Visible is what we can see with our naked eye. Infrared, this microwaves, radar, and then the TV, FM radios. So visible is a very small amount of the whole electromagnetic spectrum. And it goes from about 350 nanometers, this is in the use of nanometers, to 800. And I say about because, as anything with humans, this is kind of the average. Okay, some people can see further into the ultraviolet region, others can see more into the infrared region. This is kind of the human average here. So sometimes you'll see this is actually start out at 400 to 850. Sometimes it's shifted by 50. So this is just an approximation of wavelengths here. Okay. Oops. And that is the end of this video.